Good afternoon, Year 13s. Nice to see you guys. If you can just pop a quick hello onto the chat, that'd be lovely. I'm going to get straight on with the strong bases lesson. So I'm going to share my screen. I'm going to attempt to turn off my camera. My computer's crashed once today already. Lol. But if I can figure out why, just going to quickly jump onto the YouTube channel. See if I can find my. Just going to quickly jump onto. There we go. There we go. All up and running. Amazing. Swing that over there. Pop out the chat. I'm just trying to maximize my bandwidth. There we go. We're in. Amazing. It's nice to see everyone there. Thanks, guys. That's great. Right. Oh, I'm going to attempt to turn off my camera. Okay, guys, my computer may crash. If it does, then I'll be back in 2 minutes. Oh, it stayed. Winner. Excellent. I'm back. Right. Okay, guys. On to strong bases. My laptop did not crash. Winner. Right. So we've been working through acid-base theory. I've realized now that there's another... I've got another video which calls itself Lesson 6 of acid-base theory, strong bases. I need to go back and change that. So I'll make a note of that to go and do today. But okay, so guys, we're working on strong bases today. So things like sodium hydroxide. Yeah. You do not cover any weak base calculations at EdXL, but I am going to teach you one anyway, only because EdXL in their infinite wisdom has decided to use it. I could even find you the question, I think. So I might include that one as well, but today we're focusing on strong bases. Okay, so first learning objective, understand why Kw is needed for pH of bases. Seems reasonable. Next, be able to use Kw to calculate pH. Again, very reasonable. And the last one is no, solubility. No, solubility and temperature. Solubility and temp, there we go. Affect pH of bases. Winner. Excellent. I've suddenly realized that I haven't added the solubility bit onto my YouTube channel, so I'll add that onto there as well at the end of the lesson. Okay, so strong bases. First thing that we need to mention, guys, is what are strong bases and some examples. Strong bases, e.g., sodium hydroxide, lithium hydroxide, potassium hydroxide. All the group 1 hydroxides are considered strong. Nice to remind ourselves of the definition of strong. Notice my changing color. Yeah, strong, fully ionized in water. Fully ionized in water. In water. It's French for water. Fully ionized in water. I like it. Okay. So we've known in terms of bases-wise from GCSE, we know there are lots and lots of different types of bases. So I'm just going to swing over to the left just to make a nota bene, really. Nota bene of bases. Yeah, there are lots of them. Essentially, any metal oxide is a base. Metal oxide, metal carbonate, metals themselves. Yeah, metals and the metal hydroxides. Suddenly realized I'm running out of space. Metals and metal hydroxides. So we only ever talk about the hydroxides in terms of strength. The reason being is metal oxides, and by the way, you need a couple of these. You have to know a few of these. So just to mention a couple of metal oxides that you must know about, you have to recognize sodium oxide, and you have to be able to compare it to magnesium oxide. Yeah, but although they are bases, they can react with acids. Yeah, they're not really deemed soluble. Yeah, the reason being is in reality, what's happening with these would be considered bases rather than alkalis. Yeah, they are true bases. They will react with acids, but they're not really alkalis. And if you want to talk about ionization in water, then you're talking about solubility, which means, and this is partly because they're ionic, and the idea of dissociation. We'll do a couple of equations of that in a minute. The second reason why we don't tend to talk about these is because these guys actually react with water. Yeah, they react with water to produce the metal hydroxide. Yeah, so it's just something to bear in mind. We'll come across those. Again, metals aren't soluble. They're reacting with the water themselves or reacting with the acid themselves. Metal carbonates are exactly the same, although there are a few carbonate, group 1 carbonates, which are slightly soluble. But once again, the carbonate ions are reacting with the water, and metal hydroxides are obviously what we always talk about anyway. So we can do a couple of dissociation equations. Dissociation equations for, let's just do the ones that we've got above. So we're going to put sodium hydroxide, solid. We're going to add it to water. Give me my dissociation, please. Then we can do potassium hydroxide as well. Pause the video, have a go at doing them. I know that as soon as I say pause the video, it puts in a big delay in the channel. That's fine. I won't really do an awful lot of questions on this today. I tend to do the more one-to-one questions now in the Google Meets rather than in the lessons on YouTube. So, okay, once you've had a go, so we're forming Na plus OH minus. And we recognize that this here is producing our base. This is our base or our alkali in this case. So same thing, potassium plus OH minus, and we understand that they are fully ionized in water. They dissociate completely. Now this is because they are highly soluble. Now there's a couple of them where you want to, we need to show another one, which is this one, calcium hydroxide. Can everyone pause the video and have a go at that one for me? By the way, state symbols, of course, become aqueous. Yeah, we're dissolved in water. So have a go at the dissociation of calcium hydroxide. Now, this one's important. The reason being is it's reversible because this is now partially soluble. These are deemed very soluble. You can still max out, you still hit saturation eventually, but they're very soluble. This one's going to form calcium 2 plus 2 OH minus ions. And these are both going to be aqueous. Now, this has got actually a very low solubility. Low solubility. What that means is, if we were to calculate its pH based upon the original concentration of the calcium hydroxide solution, we're going to be far closer to 7 than we would expect. And it's something to bear in mind. Yeah, low solubility means that you can't really predict. That means what this will, by the way, this will actually gain a Kb. Yeah, so that's actually the weak base dissociation constant. Okay, so I just want to clarify something as well. These are dissociation equations, and I suddenly realized I've actually made an error with you guys. The Bronsted-Lowry equation. Bronsted-Lowry talk about proton donating. So the Bronsted-Lowry equation is the idea of it reacting with water. Now this can be done, just to show you what's happening. What's happening is this, the sodium hydroxide, by the way, this is where you have to include water. This is not Lewis, I made a mistake. Reacts with water to produce, and by the way, I'll draw this out in a minute, which is going to make H2O and OH minus, just to explain what's going on here. Yeah, just to explain, here's what's actually happening. As soon as the Na plus and OH minus go into water, yeah, they dissociate. And then, of course, what happens is the OH minus ion is going to collide. I'm going to draw this out. The OH minus ion collides with the water molecules. And of course, what it's going to now do is it's going to steal a proton. This is the mechanism for proton transfer. And what you realize is you actually get exactly the same products. Yeah, we actually get these two. So in reality, these two are actually in equilibrium. So you could actually argue, got loads of base questions and bits appearing in a second, and I don't really want any of those. In reality, you could argue that H2O is actually reacting with OH minus in an equilibrium to form H2O, to form, I'll even do that, I should color code them really, forming hydroxide ions and water. But what we realize is because the reactants and products are the same, we just don't care. Yeah, we're always going to have the same concentration of OH minus ions and same concentration of water, since the reaction is a one-to-one and the products are the same. So it's just nice to mention that this equation can be done, but then of course what happens is equation would simplify. You'd actually cancel out the water because it's on both sides of the equation. Hence why you have the original dissociation equation, and these questions don't really exist. Not really a thing. Now, just to remind you of this in the acid world, so I'm going to skip past those questions. So in the acid world, we get the Diss equation. So let's do the Diss equation for HCl. Yeah, and that's just going to form H plus and Cl minus. And then we have the Bronsted-Lowry equation, which is HCl reacting with water to form H3O plus and Cl minus. Now that's a thing. Yeah. So it's just nice to remind ourselves of those odd questions when they ask you. Lots of times in Edexcel, they actually demand you to react it with water. Yeah, instead of quoting it as a Bronsted-Lowry equation, Edexcel will say, show the reaction of HCl and water. Yeah, just thought I'd let you know. Okay, so going back to strong bases. So how do we now that we kind of understand what bases are doing, what we can now do is look at how we go about calculating their pH. Yeah, so calculating, subheading, calculating pH of sodium hydroxide. Okay, so first thing we need to do is remind ourselves of pH. pH is equal to the minus log of the base 10 of the hydrogen ion concentration. Yes, definition of pH. Boom. Right, now here's the problem. In sodium hydroxide, there is no H+. Well, that's a rather odd thing then. So how could we calculate the pH of something that doesn't have it? Well, what we need is an equation that will allow us to bring H pluses and OH minuses together. And we have already met one in the form of Kw. Kw equals H plus concentration multiplied by the OH minus concentration. This is called the Kw expression of water. And what we realize is in this expression, we have got both H plus, which is needed for pH. We have OH minus, which we're going to get from the question, and we're going to get Kw as well. And of course, we all know what Kw is at room temperature anyway. On the chat, please, can you give me the Kw at room temperature, please? Right, now since we've got an equation that links these two together, all we have to do is apply it. So what is the pH of sodium hydroxide at 298 Kelvin, 1 mole per dm cubed? Let's do 100 centimeters cubed so we can do a couple of dilutions. Well done, Ivan. Thank you so much. Right. So we've got a pH. We're looking for pH. We've got a temperature. We've got a concentration. Now, it's really lovely because you guys, they do expect you to know Kw. They do not have to give it to you. They will give it to you about 8 out of 10 times, but every now and again, they'll have a second mark which includes it. Yeah, so Kw at this temperature is 1 times 10 to the minus 14. Okay, so let's run the steps. So answer. First thing, Kw equals, we always remember that the equation is worth 1 mark. Yeah, there's Kw. Step number 2, there's the first one. Step W, input my, well, hang on, oh, I need pH. I need to rearrange this. So Kw divided by the OH minus concentration will equal H plus. That's actually going to be my first mark, just so you know. I'd actually write down both because I don't remember multiple equations. Thanks, Ben. Correct. Right. Now what I can do is I've got Kw. Yeah, I can tick that one off. I've got him, and I've got the concentration of OH minus. We are making a massive assumption. We're assuming that all sodium hydroxide dissolves. Assumption, all NaOH dissolves and it is fully ionized. Because it's highly soluble, this is reasonable. Yeah, it's a low concentration, it's all dissolved, it's all disappeared. Yeah, but that is the assumption I'm having to make here. Right, now I can input my data back to red. Kw is 1 times 10 to the minus 14 over the concentration of hydroxide ions. Now, because the sodium hydroxide dissociation equation is a 1-to-1, yeah, the concentration of that one being 1 mole per dm cubed will mean that the OH minus concentration also becomes 1 mole per dm cubed. Yeah, because it's a 1-to-1 and it's fully ionized and fully dissolved. Right, so I can insert that concentration down there. That's going to give me H plus concentration. Run it through my calculator. It gives me the answer of 1 times 10 to the minus 14. And now I just minus log answer, and I will get a pH. So minus log 1 exponential minus 14, and I get a pH of 14. And there, pH 14.0. So that explains where the pH of a strong alkali comes from. We learned in year 7, the pH scale. We love the pH scale in year 7, and we see purple at 14. Now, in reality, we can go above 14, and we can see that in a very simple question. All I have to do is modify the question. So, question, calculate pH of sodium hydroxide, 2 moles per dm cubed, 298 Kelvin, 100 centimeters cubed. The volume, of course, makes no difference. I'm going to need that for my dilution question, which will always follow. Right, so answer, switch to red. Answer, first mark, Kw equals H plus multiplied by OH minus. Never learn a rearrangement. Therefore, Kw over OH minus equals H plus. Right, 1 mark. Now let's input my numbers. 1 times 10 to the minus 14, because it's at 298, over 2. Yeah, so 1 exponential minus 14 divided by 2, and I get 5 times 10 to the minus 15. Right, minus log answer, and I get a pH of 14.3. So you can go above 14. Of course you can. You just increase the concentration of the sodium hydroxide. Now, just out of curiosity, I wonder what the maximum pH is that you could achieve. So what we need to do is we need to pick which one would be the most soluble group 1 salt. Oh, that's a great question. Let's check solubility rules. Right, so first thing we want to do is we want to find the most soluble group 1 hydroxide. So what's this going to look like? Now, what we remember is that the lithium ion is tiny, getting bigger and bigger. The hydroxide ion is really small, yeah? And we remember that if they're similar in size, less soluble. Now, lithium hydroxide is still very soluble, by the way. Yeah, but potassium hydroxide should be more soluble. Should be. Soluble. Should be more so. Let's check. It's very reasonable for us to check these things. So, lithium hydroxide solubility. Let's just check. I always love to do this. So the solubility in water is 12.7 grams per 100. Okay? 12.7 grams per 100 centimeters cubed of water. Let's now check potassium hydroxide. Seems very reasonable. Let's check that one. Potassium hydroxide solubility is, come on, it's giving me a different number. It's irritating, isn't it? Oh, I hate PubChem. Don't trust PubChem very well. But come on, just give me its solubility. Molecular weight, structure, yada, 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 yada. Where are you, solubility? I'm hating this already. There we go. Solubility, 121 grams per 100. 100 and what? Holy mackerel. 121 grams. Wow, that's insane. 121 grams per 100 centimeters cubed of water. I should be doing this at A-level standard, by the way. Just turn it into the minus. There you go. Get rid of the slash. Better. Wow, that's insane. Okay, so what we can do is, because potassium hydroxide, now people are going to say, what about strontium hydroxide and cesium hydroxide? They're super expensive. It's like rubidium metal is more valuable than gold. So we're not going to do an experiment and work out the pH of rubidium hydroxide. You'd have to max it out at a saturation. So to use over 100 grams of rubidium hydroxide would be costing you an awful lot of money to be able to work out its pH. Not really worth it. So, but we've now got a max solubility of potassium hydroxide. Right, question. Okay, year 13s. Impress me, year 13. Right, what I'm going to do. So, KOH, 100 centimeters cubed, and its concentration is 121 grams per centimeter cubed. There you go. I've got 100 centimeters cubed of it. Its concentration is 100 per 100 centimeters cubed. Grams per liter. Grams per dm cubed. There we go. That's better. Right. pH at room temperature. pH at 298. Right, guys, impress me, everybody. I want you to pause the video. Now, when you've finished the problem, post your answer onto the YouTube chat so I know that everyone is taking part. Post your answer on the chat and then unpause it to see the answer. Okay. Right, so what we now need to do is we're working out the pH. So let's use our roadmap. KW equals H plus multiplied by OH minus. Reorganize. KW divided by the OH minus concentration equals H plus. Now this needs to be in moles per liter. So what this means I need to do is I need to change this bit into moles per liter. If you're not using moles of accounting particles, remember. Right. So number of moles equals gram. And what we need to do is I need to explain each of these stages very clearly. I've got 1,210 grams per liter. Right, what I need is moles per liter. Notice that the liter doesn't change. I need to get from grams to moles. Number of moles is grams over rams. Right, number of moles is equal to 1,210 grams divided by, what does KOH weigh? Well, I'm going to need a periodic table for this now, guys. Potassium, I believe, is 39.1. Yay! 39.1. So 39.1 plus 16.0 plus 1.0 gives me 56.1. So it weighs, wow, somebody's already finished it. So 56.1, yeah, so grams over rams, 1210 divided by 56.1 gives me that, gives me 21.57 moles. Right, well, the great thing is, because the DM hasn't changed, that is the same as 21.57 moles per liter. Holy moly! God, is that true? That's insane. Right, now I've got the concentration. It's absolutely bonkers. Right, let's now input it into my data bit. I've got the concentration, which is there. It's fully dissolved, fully ionized. So 1 times 10 to the minus 14 divided by 21.57 gives me 1 exponential minus 14 divided by 21.57. Gives me 4.64 times 10 to the minus 16. This is a saturated solution. Minus log answer. And I get an answer of 15.3. Yes! Check out you guys doing it faster than I did. 15.3. Look at that. Emma, Ivan, Nikita, Ben, outstanding. Well done, all of you. God, if you can do that, you're doing great. So guys, when we teach the pH scale, we should actually be going from minus 1.5 to 15.3, the max pH of saturated potassium hydroxide. Isn't that amazing chemistry? But they're awkward as hell numbers, so we just don't bother. 0 to 14 is just fine. Winner. Right. Okay. Fab. So what we can now do, go to my learning objectives. We understand, why Kw is needed for pH basis, because it links H plus and OH minus together. We can use Kw to calculate pHs. Now I just need to talk about solubility and temp effects on pHs. Okay. So now you need to look at these. So what we need to just do now, suddenly realize my writing is getting bigger and bigger and bigger and bigger and bigger. I always do this. I don't quite understand why. It's a Surface Pro problem, I'm pretty sure. Right, let's underline it, guys. Yeah. So solubility and base pH. Okay. So this question has come up in all kinds of different guises over the last few years. Yeah, the main one they seem to focus on, however, are magnesium hydroxide and calcium hydroxide. So both of these two hydroxides are partially soluble. Yeah. They're both considered to be partially soluble. Now, what we do need to make sure we do, though, is recognize our solubility rules again, like I was running before. Which one is more soluble? Pause the video, make your decision, post on the chat, unpause, please. That would be grand. Right. So the way I remember this is you need to learn. This is from AS Unit 2, Group 2 solubilities. Yeah, and you learn a rather odd set of solubilities. You learn the hydroxide ion solubility, the hydroxide solubilities, and the sulfate and the SO42 minus solubilities for Group 2. And what you then learn is you then learn to apply it: magnesium, calcium, strontium, and barium. So, and then these are all their 2+ charges. It's nice to do that. And what we realize is it's to do with the size. Yeah. And we remember that the OH minus ion, which I'll do in blue, the OH minus ion is small. The sulfate ion is large. Sulfate ion is massive. Yeah. Sulfate ion is huge. Yeah. If you want to understand why that is, that's very easy to do. Yeah, just to explain you why, because the OH minus ion is simply that, but the sulfate ion is this. And you can see the difference in size. You know, one of them's tiny and the other one's absolutely massive. Yeah. Plus, you realize that the hydrogen atom is absolutely minuscule. Yeah, the oxygen atom is relatively small, but then a fairly large sulfur at the center. So it's very small in comparison. Yeah, you've got a big sulfate compared to the tiny hydroxide. And then what you realize is it's all to do with the size of the ions. Sorry, meant to have been. Yeah, so and then we do the same thing. So magnesium, calcium, strontium, and barium, and then we get the sulfate ion. And what we remember is similar sizes are insoluble. Yeah, so barium sulfate. Barium, the test for the sulfate ion is barium, insoluble. Yeah, that's why barium is one of the most toxic ions I've got, because it can, oh, I like it. Calcium hydroxide is more soluble. Well done. So then we can go magnesium. This is crazy. This is insoluble. Yeah, low solid. So the calcium one is greater because they've got a bigger difference. Yeah, this would be considered to be insoluble. It's not. It does have a solubility. It's just very low. Yeah, very low solubility. Whereas barium sulfate is completely insoluble. Very low solubility. Right. So we can say partially, but we can say that this is more soluble than this one. Sorry. Calcium more soluble. More soluble, less soluble. Right. So what that now means is, if we were going to compare, is more soluble. Absolutely right, Ben. Solubility of group 2 metals increases down the group. You need to make sure that you remember that statement, Ben. You need to clarify it with either the word hydroxide or sulfate. Calcium hydroxide is more soluble. Thank you, Emma. Dumb question, but if the decreasing solubility of carbonates down the group, is it due to decreasing polarizing power, which explains the OH trend? Oh, what's the explanation for the OH trend? Oh, it's way more complicated than what I'd like to go into, Ria. It's to do with the fact that when you have larger ions, it has exposed. Oh, it's horribly complicated. Oh, I don't really want to get into it, if I'm honest. So if you've got a small, right, if you had a small 2+ surrounded by a massive 2-, number one, you get you get anion repulsion in the lattice. Yeah. So in this case, we're now going to get anion repulsion in the lattice, which is trying to drive it apart anyway. Plus, when water comes along and forms its ion dipole attractions, otherwise known as the enthalpy of hydrations, there's more exposed for them to be able to make those initial bonds. Does that make sense? Which means more energy can go into the lattice, making it easier to break it. When the lattice is tightly packed, the way that they are with similar sizes, yeah, what happens is that you can't, it's difficult to get exposed on the outside. Yeah, what's happening here is I only actually need those 4, don't I? If you've got this here, yeah, the water molecules are going to only be able to get 1 or 2 in because they're very small. So the enthalpy of hydration will therefore be lower because you'll have fewer molecules forming those attractions, plus you don't get the ion-ion repulsion. So it is way complicated, but just letting you know, you don't need it anyway, but it's cool to understand it. Okay, so since we now know their solubilities, what we can now do is we can make some predictions about them. So if we were to say, well, let's make a prediction. Prediction. 1 mole per dm cubed, 1 mole per dm cubed pH. Okay, so what prediction we make? Number 1 is we know their bases. Anything with hydroxide ions is a base. The pH is going to be above 7. Yeah, it's going to be above 7. And now, although we're making a massive educated guess here, increasing lattice dissociation is greater than decrease in enthalpy of hydration. I'll send you the notes later. Amazing. So what prediction will we make? Well, they're going to be above 7, group 2. Magnesium hydroxide is really very low in solubility. It's very, very low. But there's a kicker. When magnesium hydroxide dissociates, when it does dissolve, I get 2 hydroxide ions per division. So what that means is even the small number of magnesium hydroxides that do dissolve, I'm still going to get quite a few OH minuses. Same with calcium. And then what we're going to do is we're going to work it out. We're actually going to check our predictions. There we go. So what we do know is that the calcium hydroxide is more soluble. So I'm going to get more of these. So the pH will be higher. I'm going to predict that the pH of magnesium hydroxide is going to be a give or take. I'm going to predict it as being about, what would I do? Well, sodium hydroxide of 1 molar is 14. I'm going to say this is going to be something like 10, pH 10. The calcium hydroxide will be greater. I'm going to put it at 11, 12. Oh, which one do I want to go for? I'm going to go for 11. Okay, let's check them out. We can run the calculations now. Okay, so what we now need to do is find the solubilities. So, question number 4. Question 4. Okay, let's look up magnesium hydroxide first. Seems very reasonable to me. So we want magnesium hydroxide solubility. How good a singer am I? I'm boss. That's amazing. So whoa, does that say milligrams? I don't like pub chem. Too much work, pub chem. Solubility. Whoa, that is very low. They've even given it to us as well with 2 different temperatures. Booyah. I like that. Look at that, K of the solubility of products. Hope everyone realizes that's an equilibrium constant. Loving it. Right, 0.00064 grams per 100 centimeters cubed. Okay, so magnesium hydroxide. I've gone and forgotten that number already. I'm going to take 100 centimeters cubed of it. I'm going to take 1 molar. 1 mole, we're going to add. Oh, actually, hang on a minute. Because we're going to max out solubility, aren't we? So what's going to in reality happen here is if we add, right, got to think this through, a bit more complicated. Right, I've got 100 centimeters cubed of water. And I'm going to add 1 mole. I'm going to add 1 mole of magnesium hydroxide. But what we realize is that it's not going to dissolve. In fact, hardly any of it will. What is going to dissolve, blimey, got to use the solubility. Go back to this one. 0.3064. 3064. 3064 grams per 100 centimeters cubed of water. Was it that or per liter? It's usually per 100. Yes, well done. Okay. Blimey. How much is 1 mole again? Number of moles is grams over rams. Right. What's magnesium hydroxide weigh? Magnesium is 24.3 plus 16.0 times 2 plus 1.0 times 2 as well. Total number. 24.3 plus 16 plus 16 plus 1 plus 1. Total is 58.3. Wow. So 58.3 is 1 mole. Holy moly. See what I did there. Oh, 58.3. Right. Times by 1. So 1 mole is 58.3 grams. Well, there was absolutely no point in adding that much, was there? Because only that much of it will dissolve at room temperature. Holy man, so it's going to form a white milky solution. Ah, milk of magnesia. Check this out. Milk of magnesia. I'll put magnesia milk. Yeah, if any of you guys have ever suffered from heartburn, I do on a regular basis. Yeah, if you ever see milk, if you ever drink milk of magnesia, yeah, it's gross stuff. It's a white, thick liquid. Yeah, and it's just magnesium hydroxide that's been added to water, but it doesn't dissolve. So it just forms this white suspension, which is why they call it milk, because it looks like milk. If you filter that, it'll go completely clear, and you'll have most of, 99.9% of your solid on your filter paper. There will be 0.00063 grams of it dissolved, however. Right. So what we can now do is go from that 1 molar and turn it into a real concentration. So that many grams per 100 centimeters cubed. So hang on a minute, times it by 10 to put it into per liter. So 0.0064 grams per liter. Right, I want moles per liter. So I need to change that to moles, grams over rams. I've already worked out all half my problem. Grams, 0.064 over 58.3. Remember, year 13. Remember. It's not the 5th of November. What you need to remember is that is not allowed. Yeah? The mark is for 58.3. Please stop doing it. So, grams over rams, 0.0064 divided by 58.3 gives me 1 times 10. Oh, sorry. 1.0. Rounds up. 1.10 times 10 to the minus 4. Holy moly. Right, that now is the concentration in moles per dm cubed of the magnesium hydroxide, MgOH2. However, when it dissolves, that's how much dissolved. When it dissolves, I get twice as many OH minus ions times 2. It's a 1 to 2 ratio. So I'm going to multiply this number by 2. That times by 2, 2.1. I'm just scrolling right all the time. 2.2 times 10 to the minus 4 moles per dm cubed OH minus ions. Amazing. Right, let's run it through Kw. Right, Kw equals H plus multiplied by OH minus. Therefore, Kw divided by OH minus gives me H plus. Right, lob in my answers. Kw, 1 times 10 to the minus 14 divided by 2.2 times 10 to the minus 4 gives me 1 exponential minus 14 divided by 2.2 exponential minus 4, and I get an answer of 4.54. It's actually 55 times 10 to the minus 11 minus log answer. And I get a pH of 10.3. Oh, I nailed it! Nailed it! What was my prediction? Did I predict 10? Oh my God! I nailed it! Yes! Ha ha! Right. On to calcium hydroxide. Oh my goodness me, this is hard work, this, isn't it, today, folks? Blimey. Right. Let's just sub stuff in. Holy moly. Right, let's just try and do this a little bit brisker than what we were doing. Whew. No, I didn't want to do that, you stupid computer. I've just closed the tab I wanted. Calcium hydroxide. Drop time, solubility. Go on, I've got 5 minutes. 0.16 grams per 100 centimeters cubed. Right, calcium hydroxide. Switch back to black. Calcium hydroxide. I've forgotten what it was. 0.16 grams per 100 centimeters cubed of water. Right. Okay. 0.16 grams. Perfect. Right. So turn that into a liter. Yeah, turn it into a liter. 1.6 grams per liter. Right. Now change it to moles per liter. Right. So now I need to go, number of moles is grams over rams, 1.6 divided by calcium hydroxide. What's the MR of calcium hydroxide? 40.1 plus 40.1 plus 16 plus 16 plus 1 plus 1 gives me 74.1. There's my mark in my exam, folks. Do not cheat. Yeah. Next, 1.6 divided by 74.1. And I get a number of moles of 0.0216 moles that have dissolved into my 1 liter. Right, now that I've got the concentration, I need to multiply that by 2 because the dissociation produces twice as many ions. Times by 2 gives me 0.0432 moles per dm cubed for calcium hydroxide that is saturated. Right, now that's the concentration of the OH minus ions. Perfect. Now I can run it through KW. 1 times 10 to the minus 14 divided by 0.0432. Yeah, equals RH plus concentration. 1 exponential minus 14 divided by 0.0432 gives me 2.31 times 10 to the minus 13. Is someone going to beat me? I hope not. Minus log answer pH 12.6. Okay, I got that prediction wrong. But what a game. What a game. Isn't that bonkers? That's cool, that. 12. I'll take 12. I'll even put 0.6. It's cool to do that, and 10.3. Nailed it. That was cool. Oh, I was miles off with the calcium. Just didn't realize how much more soluble it was. It's way more soluble, about 100-fold more soluble. That's bonkers. That's cool. Right. So we've now talked about solubility. We recognize that it affects the pH of our bases. Yeah. I'm tempted to do temperature. I feel like I should. So what happens with temperature? I know that you guys got another lesson. Guys, I'll finish this off next lesson. I'll end it there. Whoa, now that was an insane lesson. Let's turn on my camera. Enable. Don't crash on me. Okay, close. Start cam. It's going to go to the back of it. I know it is. Whoa, I'm back. Winner. Stop screen. Yeah, I'll stop screen. Perfect. Guys, I'm back. Right, guys, I hope you found it useful. I know it was hard, that. But cool, right? We did some really cool chemistry there. That was boss. Anyway, I'm going to leave it. This is my new favorite game. That's funny. I'm glad you enjoyed that, Ben. Ben, do me a favor. Run the calculation on rubidium hydroxide for me. See if you can tell me what the max pH is of that guy. I'll see you guys all soon. Have a great rest of your day.